Hey folks, this is Captain Jones here to talk to you about the multiplication program. So this is the part of chapter 4 where we finally start to put together our instructions to do something useful. We got two goals today, and hopefully at the end of this lesson you'll be able to trace this program and actually kind of see how it's working. And then along the way, there's kind of one important feature. We're going to talk about how the program is calculating the correct PC offset for the load and the branch instructions. All right, so let's get started. Okay, so here's section 4.4 is our multiplication algorithm. The key here comes from the fact that we can approximate multiplication with repeated additions, right? 5 times 4 is effectively the same as 5 plus 5 plus 5 plus 5, 4 fives. And so we're going to take advantage of this fact to write this program that just uses addition in order to perform this multiplication. Okay, so then so the program is down here, right? But the last kind of critical part to helping understand this is described in this paragraph here, where it sort of tells us what each of our registers are doing. So we're using registers 1, 2, and 3. These are really key. So register 1 is going to be the there's terms for that. I'm going to get it wrong. We'll call it the multiplier. And register 2 is going to be I think the other one's the multiplicand. Really stretching my brain here. Multiplicand. Which might be something like 5 and 4, right? R3 is going to be the place where we store effectively our result. And so this is the register into which we will be adding 5. Right? So you can see here a flow chart for our program. This program assumes that that the first value being multiplied is stored in memory location 3007, and the second value is stored in memory 3008. So we're going to take those two values out of memory and load them into register 1 and register 2. And then we're also going to ensure that register 3 starts out at 0, so we don't get any garbage in there when we're computing our result. Once those are sort of set up, then we start our main little algorithm. The heart of it is this box here, where I'm going to take the multiplier, R1, and on each time through, add it to the current contents of R3. Okay, so you can imagine here, if R1, R2, R3, if R1 starts out at 5 and R2 is 4. Okay, then my first time through, I'm going to add 5 to 0, so I'll get 5 in R3. The next time through, I'm going to add 10. The next time through, I'm going to add 15, and so on. Okay. Each time through, I'm going to subtract 1 from R2. So R2, which started off at 4, goes down to 3, then 2, then 1, and finally 0. And it's when it equals 0 that I sort of know I'm finished with my multiplication, right? So if I put a 5 here, the R2, if it's 4, goes down to 3. Once this goes to 10, 3 goes to 2, 10 goes to 15, 2 goes to 1, 15 goes to 20, 1 goes to 0. That's the end of my multiplication, and so I stop my program. So I'm subtracting 1 from in this case, the multiplicand, whatever is the other value, every time I add R1 to R3. Okay, and here are the instructions that actually implement this program. So here I'm taking the value out of memory 3007 and loading it into R1, 3008 into R2. I'm clearing R3, so these first 3 lines correspond to this block right here, this first chunk of code. These 2 instructions here are my load instructions. All right. So I've got the load opcode 0010, and I'm specifying in the first case register 1, in the second case register 2. And recall from this instruction that bits 8 to 0, these specify the PC offset where I'm going to find that value in memory. So for this first instruction here, we're gonna assume in this class, we'll explain why later, the first instruction of basically all of our programs is at hex 3000. So I'm load instructions at 3000, and I'm trying to get this value here in 3007. One thing we cannot forget is that when this load instruction is executing, the program counter has already been incremented, right? But that happens in the very first phase of the fetch the fetch phase. So, so the program counter, when this thing is executing, is pointing to 3001. I need to add to that value 1, 2, 3, 4, 5, 6. The program counter plus 6 will equal 3007, which is where I'm going to find that memory location. So the value I put in my offset here is 6. And I do the same thing effectively for R2. The value happens to be the same because my instruction is 1 lower and my memory value is 1 lower, so the offset ends up being the same. R3 on line at memory location 3002, R3 is cleared. I ask you a question in the exercise about what's going on, how this is happening, so I'll leave you to figure that out. And then I've got my instructions here that are going to add R1 to R3, subtract 1 from R2, and then branch as long as the value in R2 is not 0. It's very important that this branch come right after R2 because recall that all branch is doing is checking a look at the condition codes to see if we're going to branch or not. And what we want to do is specifically branch on the value of R2. So something that sort of like sets R2 has, it's very important that that's the instruction right prior to the branch, so that's the value we're testing. So you can see here I got my branch instruction, or my branch opcode 0000. I'm testing if it's not 0, so my condition code is 101. And as long as the value is not 0 from my flowchart here, then I want to go back to executing this instruction where I add a value to R3. So that instruction happens to be here. All right. The branch instruction is 3005. Recall that when this is executing, the program counter will have already been incremented. So what I need to do is subtract from the program counter 1, 2, 3. 3 values to get to this instruction here, which is specified, here, 3003. And so if you look at this value, this is, if I'm not mistaken, this is -3. This signed integer value right here. So so I formulate that offset by sort of figuring out where my program counter is and where I want it to go if I'm taking this branch. As soon as R2 is 0, this condition is false. I will not execute that branch, and then I execute my last instruction here at 3006, which is the halt instruction, also known as trap 25. And in this manner, I should be able to store effectively whatever 2 values I want in these 2 memory locations, 3007, 3008, and then run this code and observe the result of that multiplication in R3. I think that's all I got, folks. So with that, I'll see you next time.